Hey guys, chapter 5. So this is going to be the most fun chapter in all of statistics. This is going to be our chapter on probability. And the reason it's so much fun is because you get to see like how different probabilities play out. So what the probability of getting four of a kind in poker, or the probability of flipping a coin and it landing on heads. So stuff like that. So from here, chapter 5, 5.1 is a probability rule, so just introducing us into probability. And starting with the law of large numbers. So the word random suggests an unpredictable result or outcome. Simulation is a technique used to recreate a random event. Simulations can be tactical, as in physically flipping a coin, or virtual, using a computer to pretend to flip a coin for you. In both instances, the goal of the simulation is to measure how often a certain outcome, such as heads in flipping a coin, is observed. So looking at this, looking at the different outcomes. So to see this idea, suppose we flip a coin 100 times and compute the proportions of heads observed after each toss of the coin. The first flip, suppose, say the first flip is tails, so the proportion of heads is going to be 0 out of the one flip, so that would be 0. For the second flip, it's heads, so the proportion of heads would be 1 out of the 2 flips, so that's 0.5. The third flip, suppose it's heads, so the proportion of that one is going to be 2 heads out of the 3 that were flipped, so that would be the 0.667. And so on. So we had 2 different people do this. So 2 different people flipped a coin a bunch of times and it landed on heads, landed on tails. So here we could see that with this scenario, 0, 1, and then 2, we had 0 the first flip, 50% on the second flip. The third flip gave us this one. I'm going to guess that this one here is the fourth flip, but we kept doing that until we ran that scenario 100 times, because that's what it said up here. Whereas these people, or this group of people, they did this and it landed. This is the data that they ended up getting. So at times they flipped more heads, at times they flipped more tails, but after a lot of rounds, they started getting really close to 0.5. So the graph in figure A and figure B illustrates a random process. A random process represents the scenarios where the outcome of any particular trial or experiment or trial of an experiment is unknown, but the proportion or relative frequency in this case, a particular outcome is observed approaches a specific value as the number of trials increases. So here, the probability is a measure of the likelihood of a random phenomenon or chance behavior occurring. Probability deals with the experiments that yield random short-term results or outcomes, yet reveal long-term predictability. The long-term proportion in which a certain outcome is observed is the probability of that outcome. And the law of large numbers, as the numbers of repetitions of a probability experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of the outcome. So if we go back, do they show? No, they don't really show it. So if you look back at this example, the probability, the true probability of getting, flipping a coin and it landing on heads is 1 out of 2, because there's only 1 head out of the 2-sided coin. So notice that here, after we keep running this scenario, we start getting closer and closer. We did pop up a little bit, but we got closer and closer to 0.5, which is the true probability of flipping a coin and it landing on heads. And same thing over here. So they kind of fell down a little bit, popped up, fell back down, but over time, the numbers started getting closer and closer to 0.5. And that's due to the law of large numbers, because we ran that scenario 100 times. Let's see. The law of large numbers is often interpreted as a non-existent law called the law of averages by folks who misunderstand the law of large numbers. So not law of averages, this is law of large numbers. It could be confused with large numbers as in 5 million or something like that. But no, law of large numbers is just us repeating that trial a large number of times. In probability, an experiment is any process with uncertain results that can be repeated. So the sample space, denoted as S, of a probability experiment is a collection of all possible outcomes. An event is any collection of outcomes from a probability experiment. An event may consist of one outcome or more than one outcome. We will denote events with one outcome, sometimes called simple events. In general, events are denoted using capital letters such as E. So sample space, if we think of a sample space of flipping a coin, our sample space would be heads and also tails. So that's the two different possibilities that we could possibly have. An event is us flipping a coin and it landing on heads, or us flipping a coin and it landing on tails. So we have two separate events based on that. Now, one more thing, they say that it could be one outcome or more than one outcome. Say we flip one coin 2 times. So the sample space there is going to be a little bit different. Now we have to show every different possibility that we have there. We have the possibility of flipping 2 heads, or we have the possibility of flipping 2 tails. We also have the possibility of flipping tails, then heads, and we have the possibility of flipping heads, then tails. So those are all the different possibilities for the sample space of flipping a coin 2 times. And the outcome is, so one outcome or more than one outcome. It just depends on how the question is asked. And we'll see that here in the future in chapter 5. All right, next, a probability experiment consists of rolling a single fair die. Identify the outcomes of the probability experiment. So the outcomes here are every single different possibility of rolling this dice. So event 1 would be us rolling a 1, event 2 would be us rolling a 2, event 3, rolling a 3, all the way up to event 6, us rolling a 6. And remember, a dice or a die only has 6 sides. So that's why we have 6 different events, because you can't land on 2 sides at once. You can't land on a corner or anything. So you always land on like a perfectly flat surface. And now determine the sample space. So remember, we said that there were 6 sides to a die. Our sample space is going to be 1 through 6. So us counting each of the dots on the sides. So we have 1 dot, we have 2 dots, all the way up to 6 dots representing the 6 different sides of that die. Part C, define the event E, rolling an even number. So notice that, remember we said that our sample space was 1 through 6. Us rolling an even number is going to be simply that. 1 is not even, 2 is even, 3 is not even, 4 is, 5 is not, 6 is. So out of the 6 different possible outcomes, 1, 2, 3 of them are going to be us rolling an even number. And that's exactly what we have here. Event E, rolling an even number, us rolling a 2, 4, or 6. A fair die is one in which each possible outcome is equally likely. So for example, rolling a 2 is just as likely as rolling a 5. So we contrast this with a loaded die, or contradict this with a loaded die. So a loaded die would be, I'm just imagining watching a TikTok of them doing like the resin pours and everything. So creating a die and putting like a little bit of weight to one of the corners or one of the faces, that's going to force the die to not be fair anymore. It's not going to be, it's going to favor one of the sides more than it does the other. So there, it's not equally likely of having the same amount of, or having the same outcome of being selected. So here we wouldn't be able to do that. So a fair die would be us having a regular die where each side is equally likely to happen. A loaded die is us not having an equal chance of being selected. Applying the rules of probability. Okay, so rules of probability. So the probability of any event E, denoted P of E, must be greater than or equal to 1 and less than or equal, greater than or equal to 0, less than or equal to 1. So that is, and this is inclusively, so 0 less than or equal to the probability of E, less than or equal to 1. The second condition is the sum of the probabilities of all the outcomes must equal 1. So that is if the sample space S is equal to event 1, event 2, event all the way up to event N, then the probability of event 1 plus the probability of event 2 plus the probability of event all the way up to N, the sum of all of those should equal 1. If those two rules are satisfied, then we have a probability model. And a probability model lists the possible outcomes of a probability experiment, and each outcome's probability, a probability model must satisfy the rules 1 and 2 of the probabilities, of the rules of probabilities. So looking at this, the color of plain M&M chocolate candy can be brown, yellow, blue, orange, green. Suppose a candy is randomly selected from a bag. Table 1 shows each color and the probability of that color. So let's see if this is a probability model. So remember, there are two conditions that have to be met. So the first condition is that each of the probabilities should be between 1 and 0. So now let's look at this. All of the, anything smaller than 1. So what we're going to look for is smaller than 1 or smaller than 0 or greater than 1. If we find anything smaller than 0 or greater than 1, it's not here in the middle of the probability of this statement. So therefore, our conditions would not be met. So looking at this, a number smaller than 0 is going to be a negative number. So we could see here that we have no negative numbers here. So that part is met. The next one has to be less than 1. So any number greater than 1 is going to have a 1 right before the decimal. These are all zeros. So these are all numbers that are less than 1. So because of that, we could say that this one is, this condition is satisfied. The second is that the sum of all the probabilities is equal to 1. And now what we could do is take this over to Excel. And we could have Excel do the work for us. So here, insert data from table. From file. And just checking these numbers out, looks good. Insert data anyway. And now here, what we're looking for is the probability of all of these different probabilities, or the sum of all those probabilities. So sum of the probability of E all right, sum of the probability of E is going to be equal to the sum of all these probabilities, and it's equal to 1. So the sum of the probability of E is equal to 1. So those two are satisfied. So because those two are satisfied, the two conditions are satisfied. This represents a probability model. And there we go. So to verify this is a probability model, we must show that rules 1 and 2 are satisfied. Each probability is greater than 0 and less than or equal to 1. So rule 1 is satisfied. We added everything together, that was equal to 1. So rule 2 was satisfied. And the table is an example of a probability model. Awesome. So now we're going to talk about impossible and certain. So if an event is impossible, the probability of the event is 0. If an event is certain, the probability of the event is 1. So impossible would be something that will never be likely to happen. And I always like using the example, like I'm not a runner. I don't run. I prefer to lift weights. So there is a 0% probability that I will wake up in the morning and enjoy running. So that's an impossible probability at this moment. An event is certain, or is a certainty if the probability is equal to 1. So a certain event would be me waking up and brushing my teeth. So I brush my teeth every day. So that's 100% certain to happen. That's going to be the probability of 1. So 100%. And the probability of me enjoying a run would be 0, at least at this point of my life that I don't run anymore. An unusual event is an event that has a low probability of occurring. So an unusual event would be something like winning the lottery. So an unusual event, so even with the lottery, I believe that the chances of winning the lottery are like I believe it was like 1.3 million or 0. What was it? Can't remember off the top of my head. We might see an example similar to that in this chapter. But that's an unusual event. It's very, very, very unlikely to happen, but it still has a possibility of happening. Next, compute and interpret probabilities using the empirical method. So approximating probabilities using the empirical approach. The probability of an event E is approximately the number of times event E is observed divided by the number of repetitions of the experiment. So again, it's kind of like the relative frequency. That's the best way we could describe it. So it's going to be the frequency of E divided by the total number of trials, or the total number of trials of the experiment. Yeah. All right, so looking at this, an insurance agent currently insures 182 teenagers, ages 16 to 19. Last year, 24 of the teenagers had to file a claim on their auto policy. Based on these results, the probability that a teenager will file a claim on his or her auto policy in a given year is that. So looking at these numbers, what they did is, let me just write this down. So currently insured, we have 182 teens. Teen drivers ages 16 to 19. Last year, 24 of the teenagers had to file a claim. So 24 claims. And now the question here would be, I know they didn't state the question, but here the question would be, let's get a different color. So what is a probability? What is the probability of, not that. What is the probability of randomly selecting a teen that filed a claim. So now based on that, we could come over here. Let's get a new page. So 182 teens, or let's do teens 182 claims 24. So now the probability of claims or probability of event E happening. That's equal to the number of people that wrote claim, or not wrote claims, that filed claims divided by the total number of people. And that's how they got that 0.13 or 0.132. And lastly, what they wanted to talk about is for every 100 insured teenagers, or for every 100 insured teenage drivers, we expect about 13 to have a claim on their auto policy. So what they did is, out of 100, they got this number here. And because that's a probability, that's a proportion, we would multiply 100, and that's how they got 13. So out of 100, 13. So for every 100 insured teenagers, we expect about 13 of them to have a claim on their auto policy. And this is like the start of inferential statistics. We could take estimates of the estimates from a sample and expand it to the population. It's not going to be exact, but it'll give us an idea. Next, the data in table 2 represents the results of a survey in which 200 people are asked their means of travel to work. Use a survey data to build a probability model for means of travel to work. So let's grab this data. And let's build a probability model. Okay, let's skip to me. And now we have this right here. Let's make this bold so it doesn't confuse us at all. This will be our total. It should be bold. So total. So now the total would be the sum of all of these people, right? So they asked, I don't know how many people, 153 of them said that they drive alone. 22 of them said that they carpool. 10 said that they use public transportation, so on. So out of all the people, we're going to get the sum of all these people to see how many people they interviewed. And now from here, we would have our frequency and our relative frequency. So not even relative frequency, but what do they call it? Let me see what they call it. Probability. So probability of X. And here the probability of X is going to be these values right here. Probability of driving alone, probability of carpooling, probability of using public transportation, and so on. So from here, the probability, remember the probability was the number of the events happening. So number of event E, and we're dividing this by the total. So equal to this, oh, not that one, this one here, equal to this here divided by the total. And since the total is, it's going to be the exact same for each of these values, we're going to put dollar signs around that letter. And from here, grab the corner and drag it down. And just to make sure, cool, okay, that works. So each of these values divided by 200, and that's how we got the probability model here. And now just so that we could get a little bit more practice in, let's look at our two different conditions that have to be met. So the first one is that all the probabilities are between 0 and 1. And the second one is that the sum of all the probabilities are equal to 1. And this is just more food for thought. You guys don't have to do this, but we could get in the habit of doing it. So remember, anything less than 0 is not going to satisfy this condition. So let's look for numbers that are less than 0. And numbers that are less than 0 are going to be negative. So all of these look to be positive. So we're good there. And now let's look at this side. So numbers greater than 1. Numbers greater than 1 in this form are going to be 1 followed by some other number or anything higher than that. All of these are 0, decimals, some other value. So all of these are less than 1. So this condition is met. Awesome. And now we have to see if this condition is met, that the sum of all the probabilities is equal to 1. So here we're going to say equal to sum of these values. Perfect. So the sum of all of those is equal to 1. So here we have successfully created a probability model. And it's perfect. So let's see what they said over here. So probability, so we look at all of these. When we added all of them together, it was equal to 200. And here they didn't really show how they got these numbers. They just divided this by 200 and got each of these values. Perfect. So the individuals can be thought of as trials of the probability experiment. So remember, each trial was independent, and what else? Yeah, each trial was independent and equally likely to happen. We just so happen to choose these 200 different people. We compute the relative frequency of their outcomes similarly and obtain the probability model in table 3. Beautiful. All right, so part B, from table 3, we estimate the probability to be, and let's see what the questions are. So use a survey to build a probability model. We did. Estimate the probability that a randomly selected individual carpools to work. So probability of carpool. We're looking at B, and B is probability of carpool. And that's going to be equal to carpool 22 out of 200 or 0.11. So here it's 0.11. So the probability would be 11%, or we could just say that the probability is 0.11. Let's see what they said. 0.11, and they actually gave us a little bit of interpretation. So we interpret the results by saying if we were to survey 100 people, we would expect about 11 to carpool. So from here, all they did is out of 100, so equal to this value here, and we're multiplying that by 100. And we got 11. So because of that, if we randomly select 100 people, or randomly interview 100 people, we would expect about 11 of them to carpool to work. And we have C. And C, would it be unusual to randomly select an individual who walks to work? So we're going to look at probability of walking to work. So that's equal to probability of walk. There's 5 people out of the 200, so 0.25. And now let's see out of 100. So out of 100, this is equal to 0.25. And we multiply that by 100 and 2.5. So what the book actually did is instead of 100, they said 1,000. And that would be 25 out of 1,000. So now kind of mocking or copying what we did up here. If we randomly interview 1,000 people, we would expect about 25 of them to walk to work. And there we go. So this here would be the answer to part A, to part B, and to part C. Perfect. So now compute and interpret probabilities using the classical method. A classical method of computing probabilities requires equally likely outcomes. An experiment is said to have equally likely outcomes when each simple event has the same probability of occurring. So here, computing the probability using the classical method, if an experiment has n equally likely outcomes, and if the number of ways an event E can occur is m, then the probability of E, denoted P of E, is equal to the number of ways E can occur divided by the number of possible outcomes, or m divided by n. Another way we could think of it is the number of event E's happening divided by the number of the sample space. A pair of fair dice is rolled. Fair die are die which each outcome is equally likely to happen. So A, compute the probability of rolling a 7. So what we do is we look at all the possibilities of rolling the first die and all the possibilities of rolling that second die and comparing the two. We're taking the sum of those and seeing what those values are. So let's take a look at how that would look here. So here we could start with the different possibilities for rolling the first die. So 1, 2, 3. I see what I did. 1, 2, 3, 4, 5, 6. And this way it's 1, 2, 3, 4, 5, and 6, because we have 6 different sides to each of the dice. And we'll make these bold just so we could differentiate between the solutions. And now we could do this by adding those two values together. So equal to 1 plus 1. And similarly, we could just start with this part. So putting dollar signs around B, which is this value here, and bringing down the corner from corner down. And I'll do the rest of this off camera so you guys won't see that boring stuff. Okay, so now that we have all of that done here, we could continue. So that is this compute a probability of actually no, not yet. Compute the probability of rolling a 7. So we're going to think of all the different possible ways that we can roll a 7 divided by the total number of ways. So again, probability of event E is equal to the number of ways event E happens divided by the number of the sample space. Number of ways event E happens divided by the number of the sample space. There we go. All right, so number of ways event E happenings, number of ways that we could roll a 7. So we have 1, 2, 3, 4, 5, and 6. So that's going to be 6. And actually, let's do this over here. So probability of rolling a 7 is equal to 6 out of the entirety. We have 1, 2, 3, 4, 5, 6 by 1, 2, 3, 4, 5, 6. So 6 times 6 gives us 36. So there's 36 total different ways of rolling all of this. And if you guys don't remember that part, all you have to do is like add all of these. So we have 6, 12, 18, 24, 30, 36. All right. So that's our probability of rolling this. We could simplify this and divide both top and bottom by 6. Both top and bottom are divisible by 6. And 6 divided by 6 gives us 1. 36 divided by 6 gives us 6. And from here, we could plug it into our calculator. Oh, hey, actually, we're on Excel, so it has its own calculator. So equal to 1 divided by 6, and that's 0.1667. So approximately 0.1667. And there we go. That's the probability of rolling a 7. So let's clear all this out and write that over to the side. Probability of rolling a 7 is equal to 0.1667. All right, so that takes care of the first question, compute the probability of rolling a 7. Part B, compute the probability of rolling snake eyes. That is, compute the probability of rolling a 2. So quick little recap. Probability of rolling a 2, the only way that we could roll a 2 is by rolling 2 ones, because the smallest number that we have here is 1. Smallest numbers that we have here are 1s, and if the 1s are on both of the dies, that's the smallest number that we could get to. Similarly, the largest number that we could get to is 12, because 6 plus 6 gives us that 12 right there. So again, snake eyes are just those right there. I'm not exactly sure why they call them snake eyes, but that's what they're called. So now the probability of rolling a 2 is equal to, let's see, we have that 2 here, and that's the only 2 that we have. The only way that we could roll a 2 is by rolling 2 1s. And that's 1 out of the entire 36. And here we could plug this into our calculator, 1 out of 36. That's a smaller probability. Actually, no, let's leave that there. This is approximately equal to 0.2 or 0.0278. 778 or 78. All right, and didn't draw my point. Okay, there we go. And let's see what else we need. Comment on the likelihood of rolling 7 versus rolling a 2. So likelihood of rolling a 7, let's use our highlighter. So likelihood of rolling a 2 is going to be just this one right here. So just that 2 right there. However, the likelihood of rolling a 7, so likelihood of rolling a 7, we have this one here, 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 and here. Since there are 6 different ways to roll a 7 and only 1 different way to roll a 2, the likelihood of rolling a 7 is 6 times more likely than the likelihood of rolling a 2. So since there is 1 way of rolling a 2 and 6 ways of rolling a 7, the likelihood of rolling a 7 is 6 times more likely than rolling a 2. And I do believe that's it. See if we missed anything. So we got that. Sample space is 36. So now probability of rolling a 7 versus probability of rolling a 2. And part C, they say, since the probability of rolling a 7 is 6 out of 36, probability of rolling a 2 is 1 out of 36, rolling a 7 is 6 times as likely as rolling a 2. In other words, in 36 rolls of the dice, we expect to observe about 6 7s and only 1 2. Okay, so looking at this, Sophia has 3 tickets to a concert, but Yolanda, Michael, Kevin, and Marissa all want to go to the concert with her. To be fair, Sophia randomly selects 2 people who go to the or who can go with her. A, determine the sample space of the experiment. In other words, list all possible simple random samples of size 2. Part B, compute the probability of the event that Michael and Kevin attend the concert. C, compute the probability of the event Marissa attends the concert. And D, interpret the probability of C. All right, starting off with the sample space. Let's see, do we have enough room? Actually, yeah, we have room. All right, so for right now, we are going to ignore this. I know I just highlighted that. Much better. So let's ignore this and think of the sample space. So the sample space were all the friends, which were Yolanda, Michael, Marissa, and Kevin. So Yolanda, Michael, Yolanda, Marissa, Michael, Marissa, Kevin. All right, so looks like it's going to be these right here. So now from here, what we're going to do is match everyone up with each other. So just to abbreviate, we'll say YO for your Yolanda, MI for Michael, MA for Marissa, and KE for Kevin. So our sample space is going to consist of 2 pairs. So all of the samples of size n equaling 2. So the first one, we can match the first 2. We could say Yolanda and Michael, or Yolanda and Michael. Then we could say Yolanda and Marissa. Then lastly, Yolanda and Kevin. So now we have all the different possibilities with Yolanda. Now let's move on to Michael. So the next possibility is going to be Michael and Yolanda. So we could match Michael up with Yolanda, but we already have that right here. So Yolanda and Michael is going to be the same as Michael and Yolanda. So Michael and Marissa. And Michael and Kevin. And lastly, we're going to look at the possibilities with Marissa. So Marissa and Yolanda, we have that one. Marissa and Michael, we have that one. We just need Marissa and Kevin. So Marissa and Kevin. So we have those 6 different possibilities. Of people. All right, so from here, that is our entire sample space. So all the different possibilities of sides n equaling 2. And that ends up being this list right here. So perfect. All right, so now we finished out our sample space. And now the next question was, compute the probability of the event Michael and Kevin attend the concert. So Michael and Kevin. So Michael is here, but Kevin is not there. Michael and Marissa, no. Michael is here, but not Kevin. Kevin is here, but not Michael. Michael and Kevin are here together. Kevin is here, but not Michael. All right, so the only way that we have Michael and Kevin going is going to be this one right here. So the question was a probability of Michael and Kevin attending. So probability of Michael and Kevin, that's 1 out of the entire 6 different possibilities. So that's our probability of Michael and Kevin attending. Part C, compute the probability of the event Marissa attends a concert. So now we're looking at the probability of simply Marissa. There's only 1 R. So probability of Marissa. Is Marissa in this first one? No, so we don't have to count that one. Is Marissa in that second one? Yes, so we'll count that one. The third one here, yes. Second column, the first one, no, she's not there. Michael and Kevin, no. Kevin and Marissa, yes. So I see Marissa's name in 1, 2, and 3 different places. So because of that, there's a 3 out of 6 chance that Marissa actually attends. So there we go. And part D, interpret the probability. All right, since we have this is equal to, we could simplify this by dividing both top and bottom by 3. And then we have 3 divided by 3 is 1. 6 divided by 3 is 2. And this gives us a 0.5 probability. All right, so clear that out and let's see if we missed anything. So we have 6, our sample space is 6. There is only one way that Kevin and Michael and Kevin attend the concert. Therefore, the probability that Michael and Kevin attend the concert is a 1 out of 6 chance. Part C, we have n equaling 6, and there are 3 ways that Marissa attends a concert. So the probability that Marissa attends a concert is 3 out of 6, which is equal to 0.5, or we could even think of that as 50%. Lastly, if we conduct this experiment 1,000 times, so they keep using 1,000, we could even just use 100 or 10 in this case. So if we conduct this experiment 1,000 times, about 500 of the experiments will result in Marissa attending the concert. Or if we conduct it 100 times, 50 times, or about 50 of the experiments will result in Marissa attending the concert. All right, we have this one next. So suppose that a survey asked 500 families with 3 children to disclose the gender of their children and found that 180 of the families had 2 boys and 1 girl. Estimate the probability of having 2 boys and 1 girl in a 3-child family using the empirical method, and compute and interpret the probability of having 2 boys, 1 girl in a 3-child family using the classical method, assuming boys and girls are equally likely to occur. All right, so what we need here, let's grab all the necessary information. So we have 3-child families. Let's write that part down first. So 3-child families. And that's like the main thing here. So 500 families were surveyed. To disclose the gender of their children, found that 180 of the families had 2 boys, 1 girl. 180 had 2 boys and 1 girl. So 2 boys, 1 girl. Let's use Excel to help us out with this. All right, so families, we had 500 families, and boy, boy, girl, we had 180 of those. So now let's talk about the different probabilities. So empirical method. Empirical. So empirical used our frequencies. So it's probability of boy, boy, girl using the empirical method is the number of boy, boy, girl divided by the number of the sample space. So number of boy, boy, girl was not 500, 180, and we divided that by 500. So now empirical. So with the empirical method, we had the probability of boy, boy, girl, boy, boy, girl. And that was equal to 180 divided by 500, 0.36. So that's empirical method. Now let's talk about the, what was the other one called? Classical method. So classical method was the probability of, probability of event E is equal to the number of ways event E happens or event E can happen and the number of the sample space. So let's clear all this out and let's talk about the sample space. So we have 3 different children. So we could think of 3 different boxes. And for each of these, each of the children have an equally likely chance of happening. So since there's an equally likely chance of each of them happening, we have to look at all the different possibilities. So let's start with all of them being boys. So boy, 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 that's one possibility. Then we could think of the possibility of the first 2 being boys. Boy, boy, girl, and also of the middle child being a girl, boy, girl, girl, or boy, girl, boy, then boy, girl, girl. And that's all the different possibilities or all the different ways that we could have children, with the first one being a boy. Now we're going to look at all the different ways that we could have children, with the first one being a girl. So first one, we could say girl, boy, boy, then girl, boy, girl, 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 boy, and last one could be girl, girl, and girl. So now those are all the different ways that we could have 3 children. First one being boy, or looking at the first column and all of those being boys, looking at the second column and the first one of all of those being girls. So now from here, the classical method. So classical method is going to be the probability of boy, 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 girl. And hold on, what was it? Actually, I lied. Okay, so let's clear this up really quick. So the question here, and I'm glad that I checked. So 180 of the families had 2 boys and 1 girl. So there's more than just one different possibility with 2 boys and 1 girl. And I just erased all of them. So give me a second, I'll write these again and I'll come right back. All right, so the item in question is 2 boys and 1 girl. So these are all the different ways that we could select or that we could have 3 children households. So the first one is all boys, and then if you go across, it's all girls. Then 2 boys, 1 or boy, boy, girl, 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 boy, boy, girl, boy, girl, boy, girl, boy, girl, girl, and girl, boy, boy. So now out of all of these, we're going to highlight the ones that are 2 boys and 1 girl. So the very first one is all boys. So that's not going to be one of our possibilities. Then we have boy, boy, girl. There's 1 boy, girl, boy. That's still 2 boys, 1 girl. Boy, girl, girl. That's 1 boy and 2 girls. So that one does not fall into that category. Moving up to the next one up here, we have girl, girl, girl. That doesn't work. Girl, girl, boy. I believe that was supposed to be girl, boy, girl. No, that's girl, 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 boy. Okay, not that one either. Then we have girl, boy, boy, and that's this last one here. Just making sure. All right, looks good. All right, so now out of all of these, we have 1, 2, 3, 4, 5, 6, 7, 8. So out of this, we have 8. So the probability that we would have here is going to be equal to 1, 2, 3. So 3 out of 8, which is 0.375. 0.375 and 0.36. These 2 numbers are relatively close together. If it were anything higher than this, I would say that there might be a little something fishy going on here. But since these are relatively close together, I'd say that the empirical rule here matches, roughly matches what a classical method would give us. So looking at those 2, let's see what they say. So relative frequency, we have 180 divided by 500, and that gave us a 0.36. So the probability that a family of 3 children will have a boy and or 2 boys and 1 girl is approximately 0.36. For part B, they listed all the different possibilities for the first child. They went out and did the second child, then the third child from there. And they did something similar to what we did. We didn't have it this super fancy, but we did have something that mimicked this slightly. So to determine the sample space, construct a tree diagram to list the equally likely outcomes of the experiment. Draw 2 branches corresponding to the 2 possible outcomes. So for the first repetition, so for 2 outcomes, boy and girl, for the first repetition of the experiment, the first child, for the second child, draw 4 branches out of there. So basically we had first child, it was either a boy or a girl. With second child here, we had boy or girl. Here we had boy, girl, and then from here they did boy, girl for the third child here, boy, girl for the third child here, and boy, girl for the third child here. A little more time consuming, but it gets you your results a lot safer, you could say. All right. Part B. Find the sample space S for the experiment by following each branch to identify the possible outcomes of the experiment. So we got our sample space. Our sample space is 8. And then from here, those 8, we could say that boy, boy, there's 2 boys there, 1 girl, 2 boys, 1 girl, 2 boys, 1 girl. So those are the 3 different possibilities out of the 8 that will give us 2 boys and 1 girl. And they did that here and got that solution. All right, lastly, the probability that a family of 3 children will have 2 boys and 1 girl is 0.375. If we repeat this experiment about 1,000 times and the outcomes are equally likely to occur, having a girl is just as likely as having a boy, we would expect about 375 of the trials to result in 2 boys and 1 girl. So again, all they did was they got this number here and multiplied it by 1,000. Next is recognize and interpret these subjective probabilities. So a subjective probability of an outcome is a probability obtained on the basis of personal judgment. So it doesn't have any actual computation behind it. It just so happens to be out of your own personal judgment. For example, an economist predicts that there is going to be a 20% chance of recession next year would be a subjective probability because we can't really look into the future. We could just manage trends and from there kind of predict, make an educated guess, but it's not going to be an exact guess. Another subjective probability would be, I predict that about 80% of my students will pass the class. And that could be subjective because I have a lot of faith in you guys. You guys have been doing really awesome so far, but it's also just an educated guess. So it's not going to follow, it's not due to any trends or anything. It's just due to like my personal faith in you guys. And that's the end of our slideshow. If you guys do have any questions, send me an email. Please do not hesitate. Do not wait till the last minute, pretty please. But good luck on your homework. Bye.